Hello and welcome to today's IWCS webinar. Now I'm pleased to turn the webinar over to Ed Fitton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Dr. Theo Geussens, Global Application Technology Leader, Dow Wire and Cable from Horgen, Switzerland, who will be presenting his paper on development of a new jacket material for fiber optic mini and microcables. Dr. Theo Geussens is currently Global Applications Technology Leader for telecommunications within Dow Wire and Cable. He received his PhD in chemistry from the University of Antwerp in 1987. He joined the Dow Chemical Company in 1986 and worked in various R&D and TS&D functions and locations in blow molding, blown films, extrusion coating, and wire and cable applications. Since 2004, he works with Dow Wire and Cable, specializing on compounds for telecom installation and jacket applications. He is a member of IEEE and CIGRE. Theo, we welcome you to present at today's IWCS webinar series event.
Yes. Thank you, Ed. Thank you for the introduction. So as Ed already said, I will talk about the new jacket material which we developed for small fiber optic cables, the so-called mini and micro cables. This is, of course, not a work which I done on myself. You see here the names of my colleagues in our research center in the U.S. The structure of my presentation will be that first I will give you a little background about why we did this development, what the driver was for it. I will talk about the objectives which we want to achieve. Of course, I will show you some experimental results. We will talk also about the laser marking capability, which will be an additional feature that we can offer. And then at the end, of course, I'll give you the conclusions. What is the background of the development? Well, if you look, subscribers have a growing need for data volume, and the way to get to these higher data rates is to switch from copper cables to fiber optic cables in applications such as fiber to the distribution point, fiber to the home, fiber to the building, etc. Now, if you look, and this is something which has started in Europe, the dominant installation technique nowadays for these type of networks, so within the metropolitan areas and also for subscriber access, is cable jetting. As I said, this is something which started in Europe and at the moment is expanding into other geographies. Now, this technique of cable jetting also has some repercussions for the characteristics of the cable, because if you want to blow or jet a cable, of course you want to have a small cable which takes very little space, and a light cable, because that of course is easier to blow. As a result, you see that the sizes of the cables have become smaller, so we move into what is generally called as a mini cable or a micro cable. And just to, let's say, to explain you what a mini or a micro cable is, because sometimes you see different definitions. What I call a micro cable is basically a cable with one core, so with one buffer tube. It typically contains up to 12 fibers. It has a diameter of 2.5 to 3 millimeters, and the jacket thickness is, let's say, around 0.25 to 0.30 millimeters. Such a cable weighs about 6 kilograms per kilometer, so pretty low weight. What we call a mini cable are cables which typically have 6 to 12 cores. There is a central strength member present. There are, of course, in both type of cables, you have armored fibers as strength members. And for a mini cable, the outer diameter is, let's say, up to 11 millimeters, and the jacket thickness is a little bit thicker. It's around half a millimeter, and the weights, they go from like typically 30 kilograms per kilometer for a cable with 6 cores, and that can go up to a weight of 60 to 70 kilograms per kilometer, which is still about a quarter of what a traditional fiber optic cable with the same amount of fibers used to weigh. What are the objectives of the project which we had in developing this jacket material? Well, what we need is a jacket material which provides easy processing so that you get a smooth surface, you get low extrusion pressures, you want to have a reduced shrinkage after temperature cycling, because that will make sure that the attenuation of your cable is not increasing. You want to have a low coefficient of friction and high stiffness to give you the optimal jetting performance, so to blow your cable as far as possible. You want a high hardness, because that is typically associated with improved abuse resistance. And what we also included in this research work is that we developed a special version next to the standard black and natural version, a special version for laser marking. In this study, or in the results which I present, we used 3 materials. We used the new compound, which we developed, which will be labeled HDPE2. And we used 2 reference materials. We used an HDPE one, so another high-density polyethylene and a medium-density polyethylene. Now, the 2 reference materials which we used are both unimodal products with a broad molecular weight distribution. And you see on the slide here, they typically have a melt flow rate of 0.7. And the density is, of course, depending on the type of the polyethylene. And together with the density goes a certain crystallization temperature. The new high-density polyethylene is a bimodal material. As you can see, it has a slightly higher melt index, and we choose also to give it a higher density, and I will explain later on why we do that. Now, together with that higher density also goes a higher crystallization temperature, and that will mean that whatever you do in your extrusion process, let's say if you cool it fast, it will get frozen in faster than when you have a lower crystallization temperature. Let's first look at the rheology of these materials. As you can see on these viscosity curves, which are generated on a parallel plate rheometer, you see that the 2 reference materials, the 2 unimodal products, have quite similar viscosity curves, but you see that the viscosity curve of the new material, at the green curve on the screen, that has a slightly different form. First of all, you see that at low shear rates, there is a lower viscosity, and these viscosities are basically a reflection of the molecular weight distribution, and the lower viscosity at low shear rates indicate that we have no or a low amount of very long molecular chains, which will be important for the relaxation behavior, as I will explain later on. But you also see that at high shear rates of 100 reciprocal seconds and higher, the viscosity of the new compound is lower. And that means that when this product flows through a die at a certain rate, you will build in less stresses, and that will be important to keep the shrinkage of the material under control. Now, when you generate these rheology curves, you can also do some calculation and basically calculate a relaxation spectrum. As I said before, the new product has a lower viscosity, so builds in less shear stresses or less orientation in the melt, but you would like to have as much relaxation or as much, let's say, removal of this orientation before everything is frozen in the water bath. And as I showed in an earlier slide, the new compound, because of its higher density, has a higher crystallization temperatures, so you want to make sure that as much of these stresses are relaxed. And as you can see on this graph, which plots the relaxation modulus, which basically is directly related to the built-in stresses over time, and you see that with the new product, with the HDPE2, the green curve, that the stresses relax faster, at least like a factor 3. So what the stresses which you built in will be faster relaxed, and you will see that later on in the next slide, that will result in a low shrinkage. Let's say, since we don't have an extrusion line to make a fiber optic cable, we did a different setup. So we used a standard extruder, and we extrude the material as a kind of a thick installation over a copper wire at a constant line speed and with a constant melt temperature. And then we measure the processing properties, and in order to study, for instance, the shrinkage, we remove the conductor after extrusion so that we have basically a hollow tube. In the table which you see here, I would predominantly, you see that we run all materials more or less at the same screw speed, and what you see is that the head pressure of the new material is the lowest, indicating an easy processing, and you see the tendency of the HDPE grade having the higher head pressures to the new HDPE grade decreasing, and that is exactly also the trend which we have seen in the viscosity curve. So the lower viscosity gives you the lower head pressure. In order to measure the shrinkage, we selected not to measure post-extrusion shrinkage, but we selected to do a temperature cycle, actually 5 temperature cycles, to make sure that basically we have all the stresses which there are in the extruded layer relaxed and leading to the highest shrinkage possible. So what we did was we heated up from 40 degrees to a temperature of 100 degrees at half degree a minute, keep it there for an hour, and then basically cool down with the same temperature to 40 degrees, and repeat that then 4 times. And after these 5 cycles, we measured the length of the tube and calculated the shrinkage. And as you can see at the results at the bottom, the new HDPE clearly shows a lower shrinkage level than the medium density polyethylene and the unimodal high density polyethylene. And that was exactly what we wanted to achieve, because shrinkage is very important if you make small cables and extrude it at relatively high line speeds. As I mentioned before, apart from the rheology, we were also trying to optimize, or we were optimizing certain other properties, and we selected to make a product with a higher density, which then also automatically gives you a higher stiffness, in this case expressed as a flexural modulus. That can help in 2 things. First of all, a jacket, let's say a cable must have a certain stiffness for an optimal jetting performance, so that, for instance, you avoid a buckling inside the microduct in which you blow the cable. But on the other hand, it also provides additional protection of the optical fibers. And for micro and mini cables, I mean, that is required because all the elements in the cable are downgauged. So not only the jacket, but also, for instance, the diameter of the core of the buffer tube and its thickness. So it is important both for the blowing performance and for the protection of the optical fibers to have a stiff cable with a good crush resistance. Also, what you see with the new product is that the hardness is much higher than the other products, and you see that the hardness measured after 3 seconds expressed in short D units is at 65, which is probably about the maximum value which you can get with polyethylene. And this higher hardness means that your jacket is more abrasion resistant. And in those geographies where you, for instance, have termites, it can offer protection against certain species of termites, these which typically don't have very strong jaws. If you go, of course, to Southeast Asia, the hardness of this material might not be sufficient, and they typically use then a polyamide over jacket, which is still harder than what you can achieve with a polyethylene. Another property which is very important for the jetting performance is the coefficient of friction. And if you go into the IWCS archive and you look for articles from Willem Griffioen from Plumitas, you'll see that the coefficient of friction can directly be transferred into the blowing distance. So if you want to blow your cable over a far distance and space your manholes further, which means less labor cost, then you want to achieve a low coefficient of friction. And as the data here show, that is also what we achieved with this new high-density polyethylene jacket material. As I mentioned in my introduction, this material we will offer in standard black quality and also in a natural grade for color jacket applications. But what we see in the market is that there is, let's say, a certain trend towards applying laser marking in order to label the cables. And this laser marking technique offers some advantages over other marking techniques. I mean, it gives you an excellent mark durability, chemical and dirt resistance, and I will show you an example of this later on. It gives you a fast marking speed. It has a low maintenance cost, so maybe the purchase of the equipment itself might be a bit higher than with other techniques, but the maintenance cost is lower. You have a low environmental impact because you don't have solvents and you don't have inks. You can print very small and very fine characters. You get a good mark contrast, and you don't need to do a pre-treatment as you would have to do with inkjet printing, where you have to do a plasma treatment of the surface. So let's look a little bit more into the details of laser marking. On the left, you have a standard black jacket material, and most of you probably won't even see that there are slight laser marks. And that is basically what is already known in the industry. A standard black jacket with a typical carbon black level of 2.5 or 2.6% is not laser printable because the carbon black basically absorbs the energy of the laser beam. So we have developed a new compound which we have tested with a ytterbium fiber laser, and we tested this at 2 printing speeds, 2,000 millimeters per second, and that is the graph in the middle, and 4,000 millimeters per second, that is the graph on the right. And that should more or less, let's say, be the printing speeds which you would use at a typical line speeds which you would have for the production of micro and mini cables. And you can see that if you increase frequency and if you increase frequency of the pulse and the intensity of the pulse, of course your marking becomes clearer. And you see at a high line speed as well that the quality of the marking, of course, increases with increasing intensity. I mentioned before, one of the advantages of laser marking is that it is very difficult to remove unless you really remove the top layer of the jacket. What you see here is we took some of the plaques which we made, as I showed earlier. We determined where the best mark quality is, and then we put this plaque in a table abrasure and let's say treated it with 100 cycles. And after this treatment, we took a picture again, and you can see that on the right. So whereas in the initial plaque, the best contrast was achieved at a frequency of 60 kilohertz and 60% intensity, you see that on the plaque which was treated in table abrasion, you don't have that same quality of marking anymore, and it would become less easy to read. And you see that, and that should also not be a surprise, you see that the quality of the marking increases with the intensity of the laser light, because if you use a higher intensity, the marking will be applied deeper inside the polymer. Of course, this is all good. You reduce basically the carbon black content of the jacket, but you would still need to generate a certain UV resistance, which you have to arrange then also by adding specific additives. On this graph here, you see basically the results of xenon arc testing, which we carried on a 1.9 millimeter thick plaque, according to the ASTM procedure, which you see there. And we are measuring then the tensile properties after a certain amount of exposure. So at the moment when this presentation was made, we were at 2,000 hours. And you see here the relative elongation, so which of course originally is 100%. And in general, if you look in certain specifications, typically 80% retention of elongation is taken as the point in which you say, well, okay, this material is resistant up to this exposure time. With these slides, I've come now to basically the conclusions or the summary of the work. So we have developed a new high-density polyethylene jacket material, which is specially targeted to jacket fiber optic mini and micro cables, where we fine-tuned the rheological properties so that we get reduced jacket shrinkage and you get improved processing behavior. And we targeted a higher stiffness and a lower coefficient of friction to maintain an excellent jetting performance and protect the fibers inside the cable. And in addition to that, we developed a special black version which allows you to laser mark the jacket while still offering UV protection. With this slide, I've come to the end of my presentations, and I think we can open the forum for some questions and answers.
Yes, thank you very much, Theo. At this time, we will ask as many questions from the attendees as time permits. Starting with your first question, while you are focusing on jacketing materials in this presentation, are there any specific or unique requirements for the buffer tube materials in microcables?
That is a very good question, and of course I did indicate that these cables are down gauged, and I also said that the buffer tubes are made smaller and thinner. So also for the buffer tube materials, people are looking at stiffer materials giving more crush resistance to help protect the fiber. So it is not only optimizing the characteristics of the jacket, it is also optimizing the characteristics, for instance, of the buffer tube, or also to play with the central strength member. So all these elements which contribute to the stiffness of the cable and to the protection of the fiber.
Okay, thank you. Next, are any flame retardant properties required for jackets in microcable applications? If so, have you looked at FR HDPE options?
Let's say flame retardant jackets are required for indoor cables or for, let's say, so-called indoor-outdoor cables. So when these cables go into buildings over a certain length, the development which we have done here is, of course, focused on outdoor cables. I'm talking about metropolitan networks. I'm talking about subscriber access. For instance, let's say fiber to the distribution point. Of course, for indoor use, you need a flame retardant jacket, and there are, of course, a number of properties which you have to combine. You must have a certain loading of the flame retardant additive, and in particular, if you look to Europe, there is a request for halogen-free flame retardant materials, and then probably an HDPE, let's say, might have, if you would use an HDPE as the base resin, you might, of course, have some repercussions for the mechanical properties of the cable. But we haven't done yet any specific work on flame retardant jackets for these microcables.
Okay, thank you. Next, are any flame retardant properties required for jackets in microcable applications? Oh, I apologize. I just reread that question. My fault. Next question. I apologize. Could you please repeat the reference to the study you mentioned that correlated the coefficient of friction to the achievable blowing distance when you get a chance? Okay.
Yes. I need to look up at which IWCS conference it was, but there is certainly a paper of Willem Griffioen from Plumetas where you see a graph which basically plots the blowing distance versus the coefficient of friction. But I will have to get back to the person who asked the questions, because at the moment I cannot, of course, I cannot give the reference by heart.
Okay. Okay, thank you very much. Next question. In changing from MDPE to HDPE jacket options for micro or mini cables, does this impact any cable attenuation issues?
Well, that is exactly why we developed this product with a low shrinkage performance. The intention is, of course, that the shrinkage of the jacket, be it coming from the orientation which you put into the jacket during the extrusion process, or also coming from the crystallization when you go from a melt to the solid state. The idea is exactly to avoid an increase in attenuation.
Okay, thank you. Next question. In these applications, are there additives in the jacket composition to aid with low coefficient of friction performance? And if so, do they interfere with laser markability?
the question to that is no. There is in principle no additive in there which reduces the coefficient of friction. So the reduction of coefficient of friction for the material which we developed is a direct consequence of the higher density of the polyethylene.
Okay, thank you. Next, can this material replace PA12 on certain cable applications, especially on microcables used, for example, in Germany?
The answer to that would be yes. I don't think in Germany there are any termites. Of course, polyamide also has a low coefficient of friction. Let's say at the moment I cannot recall where that would be versus the HDPE which we have. But let's say, to my knowledge, a large part of the applications is basically covered by high-density polyethylene. The reason for that is also because polyamide is, of course, more expensive, and there might also be some availability issues. But if you want to protect your cable from the most aggressive termites, which you would find in Southeast Asia, I think in that case I would probably still say that polyamide, because of its higher hardness, so it makes it difficult for the termites to eat through the jacket, that would be an application where then polyamide is still used.
Okay, thank you. Next question. What percent carbon black does the jacket have?
That is a very good question, but that is proprietary information, so I cannot answer that one.
Okay, and the other, does the jacket meet the industry standard carbon black requirements?
If you understand that the standard carbon black requirements are 2.5% plus or minus 0.5, the answer is no.
Okay.
And that should, let's say, that is also something which I should make clear, because we had that discussion. So if you have a utility which specifies that the jacket material should contain 2.5% carbon black, then that jacket is not laser printable.
Okay, thank you. At this point, I see no more questions. So I would like to thank you, Theo, for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Theo after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, December 21st at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 67 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, September 29th through Wednesday, October 2nd, 2019 at the Charlotte Convention Center in Charlotte, North Carolina, USA. In addition, the third annual UL and IWCS China Cable and Connectivity Symposium will take place on Monday, March 25th through Wednesday, March 27th, 2019 at the Marriott Hotel City Center in Shanghai, China. please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.